Hey, welcome everyone. Mark here at Blue Glow Electronics. Today we're starting a new series that's been in high demand from you guys entitled Oscilloscopes for Audio. Okay, it's going to be a 101 type series, very practical in nature, hopefully get you kind of grounded in the day-to-day, how to work with audio equipment using an oscilloscope. And it's going to be a multi-part series. This first one today is focused on acquiring a basic oscilloscope for audio usage and some other handy bench tools that you'll likely need to get going. So this will be our 5-part syllabus for our Oscilloscopes for Audio 101 series. As we mentioned, part 1 here today, buying an oscilloscope and some other things you need to go along with that, because there's not a lot of audio work you can do with simply just an oscilloscope, okay? I also go on to mention here that this is not just for hi-fi nuts, okay? This video series should be great for people that work with guitar amplifiers, preamps, stereo receivers, anything of the audio nature. Part 2 we'll get into, it was one of my most requested when I made a Facebook post about potentially doing this series. A lot of people said, hey, I'm just not comfortable getting in there and working inside of something that has high voltages with an oscilloscope. So there again, hopefully a very practical guide on some oscilloscope safety basics and working with probes in and or around high voltages. Part 3 then we'll get into just some basic oscilloscope usage. What are all these buttons on my oscilloscope? What do they mean? What do they do? How do they work? That type thing. Part 4, we're going to get into real life use cases on the bench. So I'm going to set up some gear and we're going to do some troubleshooting and see if we can figure out maybe what's wrong, or at least walk through some audio setups here. And then part 5, which is really what I started this whole series about, but when I made a post about making part 5, a lot of people replied saying, hey, but I need this precursor stuff first. So part 5 will be a very advanced video on analyzing audio signals using an oscilloscope, looking for things like distortion, frequency response, power output, etc. So if you follows 1 through 4, you should be in a good enough place then to do part 5. So stay tuned. We hope to put this together over the next few weeks. And as I mentioned here, each video should be 30 to 60 minutes long, so a little longer than our normal videos, but I believe the content is worth it. All right. Let's dive on into this part 1 series here. All right, before we go buy an oscilloscope, we need to understand a little bit about what are they designed to do. So oscilloscopes kind of operate based on 2 functions that they display. In one domain here, they display time, and in another domain, they display voltage. Okay, so if you drew a little grid with axis and your x-axis being voltage and your y-axis here being time, that is what oscilloscopes are good at displaying. So if we're talking about in the time domain, then we need to learn how to speak hertz here. Otherwise, the measurement unit that is used to measure frequency. And so let's take a look at this. Let's consider this a 1 hertz signal. In other words, this signal oscillates or changes 1 time in 1 second. So it goes full cycle from beginning to end here and back to beginning, all in 1 second. That's considered 1 hertz. If that same thing happened twice in 1 second, then it's 2 hertz, okay? And so when we start talking audio work, we've got to realize the spectrum we're dealing with. Typically the audio range is from about 20 hertz. So in other words, your signal is varying, and it's not always a perfect sine wave like this. It could be a square wave, a triangle wave. It could just be random movement up and down of the audio signal. But either way, if it completes a cycle 20 times in a second, okay, that would be the bottom end of the audio frequency spectrum, all the way up to 20,000 times a second. That would be the high end. So kind of what's considered your bass notes go all the way up here to about 300 times a second, 300 hertz. Your mid-range goes from about 300 hertz up to about 5 kilohertz. And in this range here is where our voice falls, okay? So where you can actually hear a person's voice is in this mid-range. Then the high end, you're getting into where your tweeters come into play, cymbals, high end, that's from 5K to 20K. So we need an oscilloscope that will cover the 20K range to 20 kilohertz range. Okay, so what I just displayed for you was the audio spectrum, which is a very small part of the overall frequency spectrum here. And if you take a look here, kind of the radio broadcast spectrum here gets up into the 88 to 108 megahertz. You know, you get up here into like wireless for your house, 2.4 gigahertz, and on up until you get into X-rays and so on and so forth. So this is the whole spectrum that that is out there from a frequency standpoint. I drew a little pink line here. We need an oscilloscope that handles just this little end. Now, the reason I'm showing this picture, a lot of oscilloscopes you go to buy, they may cover from, say, here at the beginning all the way down here into the middle. And so we only need the most basic of oscilloscopes to handle this audio work. All right, so let's make our little list here of things we might need to get an audio setup going on your bench so that you could use an oscilloscope. Well, if you're going to measure the output of an amplifier or a receiver or a preamp or something, you're going to want to send something into the input of it that you know is a known quantity. So that way when you send something in on the input, you can then look at it on the output and you can compare the two, make sure they're the same and see if there's been any change. To do that, you're going to want to use a simple signal generator that covers the audio range. So basically 0 hertz, or as I mentioned earlier, 20 hertz, up to 20 kilohertz. Then you're going to want a basic oscilloscope. The good news here is even the most basic of basic, inexpensive oscilloscopes will cover from 0 hertz up to 5 megahertz. And you only need 20 kilohertz. So even the lowest end scope will cover the audio range. Many oscilloscopes will be 100 megahertz, 200 megahertz, 1 gigahertz scope. While they can cover that whole range, we really only need them to cover the 20 kilohertz part of that. You're going to need ideally something with 2 scope probe inputs, okay? You're going to want 2 oscilloscope probes. Remember, a lot of times you're going to want to compare what you're feeding in to what's coming out the other side. You're going to need some BNC to RCA alligator clips, and I'll show you this here in a minute. You're going to need some adapters here, and I'll walk you through those. Without these, it's going to be hard to connect these things practically, okay? You're going to want some type of 8 ohm non-inductive resistor, okay? And that's going to be for your dummy load, and we'll talk more about that. And you're going to want some kind of isolation transformer for your DUT. And if you don't know what that stands for, it stands for device under test. All right, as I mentioned earlier, feeding something into the device under test, i.e. the amplifier, receiver, whatever, that you're trying to do some quantitative measures with using your oscilloscope, you're going to want to feed a signal in that is a known signal. Feeding an audio signal in from, say, an iPod or something, you know, playing music, is not really good for measuring, and we'll show you that when we get to our practical bench setup video. But you're going to want a simple audio generator, and sometimes these are called function generators, sometimes they're called signal generators, sometimes they're called audio generators, but the bottom line is you're going to want something that covers the audio range well, 0 hertz up to 20 megahertz, okay? You're going to want something that covers the AF range, the audio frequency range, not the RF range, radio frequency range. And whatever you buy should be able to generate both a sine wave and a square wave. You're going to want those two at a minimum. Now, this little device on the left here, and I'll have links down below. This is something I found on Amazon. It will do everything you need, okay? Same as this probably 50-year-old RCA unit right here. And if you'll notice, it's titled audio generator. These are really common. It's an older Heathkit audio generator, and this can do your sine wave, your square wave, whatnot. This is what I use here, a B&K Precision, and while this will do a little ways into the RF range, it does a really good job down here in the audio frequency range. And you're going to want to be able to connect via BNC connectors. So if you'll notice, these units here have BNC connectors, and these do as well, but this one and these do not. You're going to need these little adapters that plug in. The little tab here on one side will be the negative. It would plug in and it would give you BNC output for this. So just some basic specs you're going to want to look for if you are going to go online and find one. You're going to want it to put out an output voltage of at least a 0.5 volt, okay? That would be considered line level. Preferably, maybe it can go on up into maybe the 20 volt range or so. you're going to want it to have an adjustable output level. So if it doesn't have a knob on it somewhere that you can grab and turn to adjust the output level, that generator is not for you. And then some of these units have a nice little switch on them that will give you 20 dB of attenuation. So in other words, you'll have a full sweep on one of the knobs, and then you could maybe flip a switch or pull the knob in or out, and it would attenuate that signal by 20 dB. And the one I use over here, I can tell you it'll do that. This little knob right here is kind of your volume knob, and if you pull it out, it gives you 20 dB of attenuation. I use that function all the time, okay? It needs to cover 10 hertz or down to 0 hertz or whatnot, all the way up to 20 kilohertz. Sometimes you'll find one of these that'll cover part of the AF range and the RF range, but it may start at 100 hertz or 200 hertz. You don't want that. You do want something that'll go all the way down to around 10 hertz. You're going to want something that has distortion specs of preferably around 0.1% or lower. Otherwise, you're feeding a lot of distortion into your device under test. And then on the output, you might be trying to measure the distortion. You don't want to add a lot of distortion from the signal you're feeding in. One that has a frequency meter is a nice thing to have. So like this one will display the frequency. This one displays the frequency. This one does, but it does it in terms of, you know, the analog dial and where you're at on the dial. Same over here. These will have little dials that do the counter, but it's showing what you want to put out, not exactly what is being put out. And then last I mentioned here, you might need some banana tube BNC adapters. Okay, so I came over to eBay and I just did a simple search for audio signal generator. You can see here some new ones that cover 0.1 hertz all the way up to 10 megahertz, and you know, these are new digital units, $139. Here's some older used ones, $34. Looks like this is a low frequency. You know, if you are buying a digital one, check on the things I mentioned around. Make sure it can put out at least a 0.5 volt. Make sure it does have the right distortion numbers. Here's an old RCA sine wave, square wave generator. And there's just lots of options because these things were made for many, many years. So there's no shortage of what you may want to use here. Just kind of look for some of the things I mentioned earlier. All right, let's get to actually selecting our oscilloscope. There's a lot of options out there, literally just as many as there are audio or signal generators. And you may say, well, wow, I'm really confused. I don't know what to go get. Well, here's the short and narrow answer. All of these will work for audio work, okay? This here is the Analog Discovery 2, which is a kind of computer-based digital oscilloscope. This here is just an old Tektronix simple 2-channel scope. Matter of fact, this was what I started out on back in college. This is a Tachi 2-channel scope, an old Ico oscilloscope. Even this old ancient looking with the round tube here will do 5 megahertz, so no worries of that. This is a modern day Rigol DS1054. I've got one of these on the bench as well. And this is the Tektronix 2246 that I like to use. Some of the differences between these starts to get into how practical they are for you, okay? So first off, I find computer-based oscilloscopes not the most practical. The reason being is you have to have this device on your bench, and then you kind of connect your probes to this, and then you connect your probes into your device under test. But then you've got to have a laptop or a computer screen there, and it takes up a lot of bench space. So that side of it, not that it's not a great scope and won't work great for you. I just find it limiting and taking up bench space and being a little awkward to work with. Whereas something like this little 2-channel scope right here fits well on the bench or maybe on a shelf above your bench and would work out well for you. If you'll notice here though, if I'm trying to measure this signal, right, and these little lines here are called gradients, and each gradient will then tie down to a meter, a setting on a switch here. You're going to have to count these 1, 2, 3 gradients, maybe 3.1 gradients. Then you got to multiply that by the value set on your scope here. And you might know because of that, because it's set on 2 volts per division, that 3.1 is really 6.2 volts. And you're going to have to do that math yourself. Whereas some oscilloscopes have the ability to measure the signal that you're reading and display the value for you. Almost all modern digital oscilloscopes do a really good job of measuring and showing values on the screen for you, Whereas if you get into some of these older scopes, it won't do that for you. Doesn't mean these scopes aren't great scopes and that they won't work well. Like I said, I used a scope like this for a good 15 years or more before I made an investment in something that at the time was much more expensive. But now, even these, because of the new digital ones, even these old analog scopes with the digital readout on them have gotten inexpensive, okay? So one question I see a lot, and I've been asked a lot, is should I get an analog oscilloscope or a digital oscilloscope or computer-based? Well, I've already talked about what I thought was the downside of the computer-based. However, if you've got a small laptop and room for it on your bench, there's nothing wrong with going with a computer-based oscilloscope, nothing at all. The analog versus digital, let's talk a little more about that. All right, let's simplify this a little bit and just call it analog versus digital, and we'll lump computer-based right into that bucket with digital oscilloscopes. So on the left here, what we have is a signal on a modern-day digital oscilloscope. And on the right here, we have a signal on a vintage tube-based with phosphor screen analog oscilloscope, okay? And you may look at this and say, wow, look at the signal here on this analog. Look how jittery it is. Look how rough it is on the edges. And then look at the signal over here on this older analog oscilloscope. Well, here's the reality. The exact same signal is being fed into these two scopes, okay? What's going on here is the older tube-based oscilloscope that sprays an electron beam onto the back of a phosphorus screen. Well, the reaction time to this screen is slower, so it has a tendency to smooth out your signal. And this is actually a more true representation of the signal being viewed than on the older analog oscilloscopes. Having said that, I still like the older analog oscilloscope because I'm an older analog kind of guy, okay? It's just what I grew up on. However, there's nothing wrong with using a digital oscilloscope. A little bit of this granularity here is the pixels on the screen, and some of it is actual noise that it's able to pick up and display. That noise came and went so fast that the screen couldn't display it over here. So EEVblog does an entire video on this topic. I'll put a link down below, and he goes into great depths on this whole phenomenon and the difference between those two. But that's just one difference between analog and digital oscilloscopes. And for me, I like the analog, but you know, I didn't grow up on modern day digital scope. So if I had, I'd probably say, well, I don't want that slow, old, unresponsive scope. I like seeing everything real lifetime here, and I would like the newer scope better. Okay, another difference between modern day digital oscilloscopes and older analog scopes is how you control the functions of the oscilloscope. And I'm speaking in generalities here, but digital oscilloscopes tend to be menu driven and button driven. Let me give you an example. On an older analog scope, if it had 4 channels, you might have 4 independent knobs for your time domain and 4 independent knobs for your voltage domain. Here, you have to push this button and then you use this one knob for channel 1. Then you would push this button and use this knob for channel 2. If you wanted to measure the peak-to-peak voltage of this blue sine wave here, you may have to push one of these buttons over here, which may bring up a menu on the screen. And then you may use this button up here to scroll up and down through that menu to say, hey, I want to measure peak to peak, okay? So it's very menu-driven, very button-driven, and sometimes that can be considered more complex and more time-consuming than to have discrete buttons and individual switches and knobs for individual functions. Now, I'm sure if I had grown up on a digital oscilloscope, I would be so good at these things that I would say this is so much more efficient and effective than those older digital analog scopes. And there's so much more I can do here because of the menu-driven capabilities. So it's kind of a what are you used to and whatnot. But I do find for audio work personally, the older analog scopes to be a little more practical and a little more time efficient. Here you can see an example of this. You know, each channel has its own little switches here. Each button has its own purpose. There are no menu-driven functionality, right? Every little capability on the oscilloscope has a button or switch for it. So if you learn every button and switch, you've learned the oscilloscope. Where the more modern digital oscilloscopes have lots of menu options, which can give you a lot more features and functionalities. Also comes with more complexity of which one do I use, when do I use what, and when. So that's why I think learning on an older analog oscilloscope may be better. And then after you've kind of got the basics, you could move forward to a more modern digital oscilloscope. Me personally, I've not quite made that jump yet. And for all the things I do analog based, these older scopes work great for me. Okay, so if you buy a scope and you buy a new one, it's certainly going to come with 2 oscilloscope probes. But if you buy an older scope, it may not. You can get this little set of probes right here on Amazon for dirt cheap, and they will serve all the purposes you need for audio work. Similarly, here you can see just different styles and kits. These are some older probes, Tektronix probes, but you basically need 2 probes to get you going. All right, there's a few other things you're going to want related to the probes that come in a kit here on Amazon. You can see the price on this entire kit is $21. And for the audio work you're going to be doing, this kit would work fine. So it's going to give you your 2 probes that you're going to need, and it's going to give you various colored rings to identify left channel or right channel or whatnot. It's also going to give you some other connections here, BNC type connectors that you could use with not necessarily the oscilloscope, but maybe with your function generator. And I'll show you here. It's going to give you a BNC to BNC, a BNC to test lead probe. And I use this little connector right here all the time because I'll inject a signal somewhere midway in the amplifier using little probes like this, okay? You'll get a BNC to alligator clip and some BNC, looks like to some type of little probes here. But great little kit for $21. I'll put a link down below. So this is where things start to get very practical, okay? You probably won't find any video out there on how to use an oscilloscope that'll teach you this kind of stuff, okay? First off, you're going to want to have a way to connect your signal generator into the amplifier that you're feeding, okay? And this is a picture of my actual bench. So this is my BK Precision, what is it, 4003A function generator that I use, okay? If you'll notice coming out of it, I've got a BNC here to a little adapter, to then another adapter, which then feeds a cable, which then allows me to plug into my stereo or my amplifier via RCA jacks. And I'll show you more on this. All right, so you're going to need a 3.5 phono to RCA, and I would say 5 or 6 feet long. If you get much longer than that, it just gets kind of clunky on your bench. And if you get shorter than that, you'll find yourself stretching it all the time. So you may wonder, why would you use the one on the left and not the one on the right? They both look like 3.5 millimeter phonos to RCAs. Well, here's why. If you'll notice the distance between this little device here that keeps the cable where it splits out at, you'll notice there's a good distance around here to this. So in other words, you could spread these RCA jacks apart maybe 10, 12, 14 inches, okay? Whereas these, if you'll notice, this thing is really short right here, and you could only spread these apart about 5 or 6 inches. Well, I run into frequently with tube amplifiers where one RCA jack is on the right-hand side of the amplifier on the back, and the other is on the left-hand side, and you need to be able to spread those out a good 10 or 12 inches. So get something where you can spread out the distance here. Up next, you're going to need a BNC male to RCA female adapter, okay? And it's a simple little device. One plugs onto your piece of equipment, which gives you an RCA jack on the other side. This was a 10-pack for $6.99 or for $11.99, and I'm not endorsing any of these products. I'm just showing you what I'm finding online. This comes with a bunch of different types of adapters that you might use for different purposes, so make your choice, but you only need one of these, so even the 10-pack is overkill, but I couldn't find anybody that sold just one. And this is the tough little booger to find. But here you can find Monoprice, and there's the part number. It's $5. But what it does is it takes one end RCA, and then it puts it into a stereo jack, but it feeds it to both sides of the stereo jack. That way, whatever you're coming out of your function generator, signal generator with, it's getting fed to both sides of the 3.5 millimeter stereo jack, which then ends up feeding the same signal into the right and left channel at the same time. So handy little gadget to have. So when you stack all three of those together, you're feeding into the BNC jack here. You are then going into the RCA adapter here to 3.5 millimeter phono, which then sends this signal out to both channels, feeding down the line and goes into your left and right channel. If you happen to notice, remember earlier, I can change the amplitude of this using this unit, and if I pull it out, it drops a 20 dB attenuator in line. Absolutely love that feature. Probably 90% of the bench testing with audio gear I do is with the cable setup I just showed you. Hey, if you happen to be a guitar guy and want to feed into your guitar, you can just change the adapters to be something that fits the larger phone jack for that. Or sometimes, coming back around to this, I might just clip on to my function generator here with this BNC connector, and then I may feed down and insert somewhere in the middle of the amplifier. So let's say maybe I'm trying to bypass the driver stage and feed directly into the output stage. I may use this little connector. So that's why having this little kit would be very handy. Okay, and finally here for your little audio bench setup, you're going to want an 8 ohm non-inductive dummy load and 2 of those, okay? And there's a couple options out there, you know. Here there's one listed that says it's non-inductive, but I also noticed that it's a wire wound resistor which has inductance, so maybe they found a way to overcome it, but that one I'm not going to go with. Parts Express has an 8 ohm 100 watt, $22. You could get 2 of those, wire them up into a little box or something, and use some banana jacks, speaker jacks like this to wire it up, and you would have the perfect output load for a bench setup. Or, you know, here's some, even for $5 you could get some 20 watt if you didn't want to go full 100 watt. This is about what I use. I actually use some Dale resistors that are really hard to find these days, so these Parts Express 8 ohm 100 watts would work perfectly for a nice bench setup. Okay, another device you're going to need if you're going to want to do a lot of oscilloscope work with audio is an isolation transformer. And you're probably going to want one of these for other purposes as well, but as it relates to audio work and oscilloscopes, typically your oscilloscopes are grounded on the inside. Thus your scope probes, the outer leads of them are grounded not only to chassis ground but back to earth ground. And in some cases for audio work, you're going to want to be able to isolate that. So you're going to want to be able to plug your device under test, i.e. the amplifier or receiver or whatnot, into one of these devices that electrically isolates it from the AC mains in your wall and separates it from the earth ground. And so all these little devices here I've got pictures of, they plug into your wall outlet, and then you plug your device under test into these devices. And what it does is it does that electrical isolation there and ground isolation. So some of these devices will have 3-prong plugs on them. I mean, it won't have 3-prong plugs, yet the device under test you may be testing requires 3-prong plug. So you might need an adapter to go from 3 prongs on your device under test into one of these. This little RCA device down here in the bottom right-hand corner is exactly what I use underneath my bench. I plug my devices under test into this. I actually feed out of one of these into one of these little 3-prong plugs. Then from that, I go up into a power strip mounted on the side of my bench. And then from that, anything I plug into that power strip, I know is isolated from earth ground at that point and electrically isolated from the AC mains. So probably want to get one of these. You can find these little units anywhere from $40 to $75 on eBay, somewhere in that range. You can buy new ones for, you know, in the $100 range type thing. So definitely something you will need. So with all that, you should have all the practical aspects you need to start doing some audio bench testing if you've obtained those components. If I were to make some recommendations on an oscilloscope, and these are not endorsements, here's some options I might point you towards. This Rigel DZ1054, it's $350. It'll go up to 50 megahertz, and it has 4 channels in it. I've got one of these on the bench I use from time to time. This one I've been actually looking at for myself, a DXOX1202G. It's basically a 70 megahertz oscilloscope, 2 channels, but it has a built-in waveform generator and it can do frequency response plots. So that's this little black Keysight unit down here. About $1,000. Maybe you want to spend that much, maybe you don't. I don't know. But I've actually been eyeing one for myself. This is what I started out on, the Tektronix T935. You can find these for like $100 a lot of times in good working condition. There again, you're going to have to count the gradients and do the math yourself. It doesn't do any on screen display. Similarly, the Tektronix 455 or 465, these things are workhorses. There's thousands of them out there. They're on the used market all the time. You can find a nice calibrated one in the $250 to $300 range. There again, doesn't have any on-screen math or display, so you'll have to count the gradients, but these things are great scopes. And then I use the 2246A here, which you can see it will measure and give you the voltage rating here. Pretty simple. And believe it or not, these used to be big time expensive scopes. Now you can get one of those fully calibrated for $300 or less. So, you know, my recommendation getting into this, either get one of these Rigels or spend the $300 or less here, all depending on your budget. Also, don't get wrapped so much around specific models like 2246. There might be a model 2256 that I'm not aware of that has the same functionality and maybe it's the same price range. Or maybe Hitachi makes a scope that has the same functionality. You know, don't get wrapped so much around the specifics here as much as I am talking in generalities about capabilities and price ranges of scopes. You don't need a $1,000 oscilloscope to do audio bench work with. All right, so I've shown you the oscilloscope options, or a few of what many are out there. I've also shown you some of the little auxiliary pieces that will make your life easy if you're trying to do some audio bench work. But in reality, the best scope for you is the one that you learn how to use and that you get comfortable with. That 2246 you see me quote over and over, it's not the best scope on the market. It's probably not even a great scope. It's just the one I've used for the last 20 years, so I know it inside and out. I'm very quick with it. I know which knob to turn when. I know which button to push when, because I've learned it very well. If I had started out 20 years ago on a certain model digital oscilloscope, I'd probably be as fast and familiar with it, and that would be my go-to scope. So whatever you pick, learn it well, learn all the intricacies of it. That will be your best friend, the one that you know and that you're comfortable with. All right, I'm going to put these links down below, and these are not necessarily endorsements by me of these products. They're just ones I know that I have bought and that work. One, I've got a link here for the Why Digital Oscilloscopes Appear Noisy. That's a good video to watch. That RCA mono to 3.5 millimeter stereo adapter, the 8-watt inductive, non-inductive dummy loads, 100 watt, the isolation transformer if you were going to buy a new one, RCA to BNC male, the SyncWire RCA cable, and the universal oscilloscope kit. I've got all those links I'll put down below for you. All right, I hope you've learned enough from this video to kind of get you going, and we're going to move to part 2 next, which will be the safety precautions and working with probes inside of gear with high voltages. So stay tuned. We'll try to get that one wrapped up here in the next week or so and get it posted online. I'm figuring about a week in between each of these videos, so hopefully over the next month we'll get all these topics covered. Hopefully this is hitting home for you guys, and stay tuned for more. Thanks everyone.